So in the last lecture, we were beginning to develop the operator sum formalism, and we saw there are three separate ways of understanding quantum operations. Of course, one was the system taking into account all the environmental interactions, and then tracing out the environment degrees of freedom if you are interested in a quantum map on the system. Or we had the slightly more abstract operator sum representation, which was a great tool for calculations. And of course, what we shall also discuss is the physically motivated axiomatic approach to quantum operations or open quantum systems, where we start by, basically an axiomatic way of saying what do we demand of a quantum operation? What should a quantum operation do, or what sort of set of states should it input and what set of output it should give? And based upon certain axioms, we come to certain conclusions regarding the properties of quantum operations. And we shall see that that covers a wide spectrum of a wide array or a range of quantum operations or physical phenomena we can describe. Of course, all three are equivalent. Axiomatic approach, the system environment dynamics, or operator sum representations are equivalent to each other, but they might offer insights, different insights into the problem at hand. So with that, we started studying the natural way of describing the quantum operations from the environment and system dynamics point of view. And over there, we started with the joint state of the system and environment. It evolved through certain unitary dynamics on both the system and environment, and then we traced out the environment variables to get just a map on the system itself. So that was one way, and that's represented below by the circuit diagram that I have an input of a system and environment in a tensor product state. There was a joint unitary dynamics, and then I leave the environment out and I get a quantum map on the system itself. So now one might ask a few questions regarding this, that what is the physical interpretation? So coming to it again, we have the system, and this is the environment degrees of freedom. We have a unitary evolution, and then we traced out the environment, which we represented as certain operators ek, or a set of basis sets for the environment, and that gave us the quantum map. Now the question is, how do we physically interpret this? So mind you, this gave us also this gave us what we called as also the operator sum representation, where my EKs were some operators just on the system space. So how do we physically interpret this guy? So one way to interpret this is the following. Consider this operation. See, you have a row system you had the initial condition of the environment, and then you had the unitary evolution. And now instead of tracing out the environment, let me measure the environment. I measure the environment using these projectors. So these are projector operators on the environment. Hilbert space. And after making such a measurement, I might ignore the environment. I might trace out the environment. So what really is happening is that in the parlance of my circuit diagram, I have the system, I have the environment, I have the unitary operator, and then I'm measuring the environment and I get a certain map on the system. So if you look at it, the state of the system that I will get is going to be based upon the projector. Let's say I measure the environment and I get K outcome. The state of the system corresponding to that is going to be, as we discussed, this guy. The entire thing we are going to write again. And of course, this needs to be normalized. So I'm going to write the normalization of it, or it's going to be the trace of this entire thing. So this is going to be the state of the system when the projector operator K is acting, or in other words, when I find the environment in this state, and this is going to be the state of the system. So, and with this probability. So the probability of the outcome is precisely this guy, which is, let me just this guy. Of course, outcome K is not the only outcome with probability Pk. So the final state of the system is actually a convex combination of all the possible outcomes with respective probabilities. Or in other words, one can also write it down as these guys. Where once again my Ek is given by exactly the same thing which I had before. So this is fantastic. I mean, and this is one of the equivalent ways of seeing this notion of quantum operations. Either we traced out the entire environment, that we did over here. And we got something across form, or the operator sum representation of the quantum map on the system by neglecting the whole environment, tracing it out. Or we can view the operator sum representation or this tracing out process as the environment being measured, and based upon each outcome I get a corresponding density matrix on the system. And of course we don't know which measurement outcome is going to occur, so the final state of the system, taking into account the probability of all possible outcomes on the environment, is given by exactly the same operator sum representation. So this is one way of physically interpreting the operator sum representation by measurements on the environment. So there is another very interesting way to view this. See what is really happening. Rho gets transformed to rho k with a probability piece of k. So in other words, I can interpret the action of the quantum operation as taking the state rho and randomly replacing it by this guy with, well, I can normalize this, doesn't matter. With probability pk is equals to so I am replacing rho by randomly by this guy, this operator, with some probability, and this process is a noisy process where I am replacing it's a kind of a noisy communication where I had a input rho, I had a noisy channel, and I get certain rho k's with probability pk's. So that's why in the parlance of communication theory, a noisy channel or a quantum operation are used analogously. That's exactly what our quantum operation is doing. Now, how it is doing might be the environment is getting measured, and based upon the outcome you replace the state by what's on the output, the effect of the measurement of the environment, and you sum over it, so on and so forth. But this is a very elegant way of seeing the quantum operation as a noisy communication channel where your input transmits to the output and some noise is added, and the sources of noise is entirely quantum. That's why you call it quantum noise. Physically, one way of interpreting quantum noise is, as we have done, measurements on the environment. So this is exactly what's happening. So as an example, we can consider an input 1 qubit state. Initially the environment is in the 0 state, and the joint unitary on the system environment is a C0 gate, and I make some measurements on the environment, and what I get on the quantum state is a quantum map. So you can check, but you can write this joint unitary C0 U as my first qubit belongs to the system and the second belongs to the environment. So I have this unitary as, by the way, this example also is in Nielsen and John. These guys. And of course, my cross operators or the operational elements of the operator sum representation are given by, let's say my environment is in the basis 1, u, 0 and 0, u, 0. This is E0, that gives me on the system, a projector on the system, and this guy is E1, that gives me the projector 1 on the system. Play around with it, put U, take the inner product with respect to the environment, bra and ket, you're going to get E1, which is just going to be a projector on the system. So therefore, my quantum map, due to the C0 gate and measuring the environment, was nothing but an operator sum representation in terms of the operator sum representation on the system, where the operator elements were just the projectors on the system. So now the question arises is that can I generalize this further? In the sense that over here I was measuring with respect to the environment. I was measuring the environment over here. Remember, my projector operators were the projectors on the environment. So further generalizing this would be, by that I mean generalize this to now interpret an operator sum representation as to interpret the quantum operation as a measurement on the joint Hilbert space of system plus environment. So now I am performing a measurement with projectors on the joint space of the system and environment. So when I am constructing projectors which are joint on the system and environment, that tells me, that would give me some information about the quantum state itself. So let's see how that materializes and what I actually mean. So I start with the joint state. Of system and environment. This is the system, this is the environment. And now, as usual, they run through. I might not always use the subscript it would be clear. I have the unitary operation, and then I make measurement, and by measurement I mean I hit them with projectors on the joint system. And of course, so this is going to be my state as a result of the outcome of measurement being m, what was the projector, and I'm going to just normalize it, the same thing. And of course, if I am just consider about the state of the system, so this is a map on the system, I'll have to trace out the environment for it. So in other words, I have a quantum operation on the system that takes into account the environmental interactions, a projective measurement on the system and environment, and then neglecting the environment. This gives me a state of the system depending upon the measurement outcome m, or the index m, measurement outcome corresponding to index m, and the final state of the system would be nothing but the quantum map applied divided by, so this is a normalized state, and the probability of outcome m is nothing but this guy, trace of the operation, which was nothing but this guy. This guy. So once again, to summarize, I can, and mind you, this gives me a quantum operation based upon a one particular outcome. Of course, there can be many outcomes are happening, so you can already see that this is a quantum operation based upon the outcome m, and this quantum operation is not trace preserving, not trace preserving, because this quantum operation only takes into account iso m rho, this quantum operation index with m only takes into account measure account one measurement outcome indexed by m, and hence is not trace preserving. There can be other outcomes with other probabilities, we don't know. So for example, if the state of the environment is this guy, that's the state of the environment, Uh, one can introduce an orthonormal basis for the system, and then one can calculate the cross representation. So what's really happening is that I had rho now times that is the state of the system environment. They are operating with a unitary operation. And then I have the projectors on the joint state. And then I have these projectors on the joint state. And then I can easily trace out the environment. So what I get in actuality is, so how would the projectors in general look? The projectors in general can look like something like something let me call them piece of prime M. So this is a projector on one of the systems, let's say on the system, and this is a projector on the environment. Or it can be other way, doesn't matter what index I use. So sorry, this was on the environment. This is on the system. So in that parlance, once I replace these projectors over here, what I get is the quantum map finally was nothing but I start with the system, the environment, which was anyways this thing. I've taken the summation of u outside, and then I had a unitary operator, and then I had the projectors onto the system environment, and this was all traced over the environment. So in other words, when the smoke clears, I get an operator sum representation like this. Where each of these operator sum representation can be regarded as square root of qj, because I need e and e dagger, so, and I have a qj, so the coefficient would be square root of qj, something sandwiched over the this guy. So this is a generalization of our initial formalism where we had an ek which was just ek u e0, where we were just taking into account measurement on the environment. This gives me a measurement on the system, the joint system of the system and environment, and I can still represent the quantum operation based upon the measurement outcome m as an operator sum representation where the operational elements are given by this guy. So this should be this over here. So now really we have represented the quantum operations and interpreted them as either the measurement happening on the environment or generalizing it, the measurement happening on the joint system, joint Hilbert space of the system and environment. So what else is remaining now? So I can ask the flip question now. System environment models for any operator sum representation. So the question is that now we have a converse problem. See, initially what we were doing was we were trying to interpret the operator sum representation as some what's really happening physically, or interacting quantum systems give rise, in a natural way to an operating sum representation. I had a row, I had an environment, they interacted with each other, and then I traced out the environment, and that gave rise to an operator sum interpretation. Now I ask you the flip questions. Given a set of EKs, can I come up with a model of system environment dynamics or interactions? So it's a flip problem in a way. Earlier I was given this thing, I came up with the operator sum representation. Now I am given the operator sum elements, and the question is, can I come up with a dynamic of the system environment interaction? So that's my question. And of course the answer certainly is yes. Let's do it for trace preserving quantum operations to start with, and the extension or the case where the quantum operations are not trace preserving, as we saw in the case of measurements, that's also possible. It's a simple extension. So what's given? So given is, I've been given operation elements. EK, and they satisfy the completeness relation. This guy. So, and what's our target? Target is that we are attempting to find an appropriate unitary operator. U to model this dynamics. So in some sense, we have to model this dynamics as I have any system state. I start with an initial given state of the environment. I have a unitary operator, and when I trace over the environment, I get a representation in terms of the operator sum elements which have been given to me. That's essentially the problem. I need to find this U. So it's not very hard to find u, what really happens is that if you look at it in terms of a matrix, uh, the matrix of u, now I'll assume in this particular case that let me, we've been so far dealing with a tensor product states of this form where the system comes first and then the environment comes. In this case, it's just convenient. I'll place the environment and the system. Doesn't really matter how I construct my tensor product. But given that thing, my representation of my u, the unitary operator, if you look at it very carefully, is just going to be a matrix of the form where this is going to be, let's say, system was d-dimensional and the environment was d-dimensional. So this is going to be a huge matrix of d square uh, by d square, and where my entries are going to be the first column. So if you look at it, this is a matrix U. Of course, I can fill up there's a huge space over here where I can fill up to make sure that U is indeed a unitary matrix. But it turns out this matrix, provided it's unitary, which I can make sure by adding here whatever I desire, this will do it. This is going to do exactly what I require from it, simply because if you see U, where I have this guy E1, E2, acting on the tensor product state of the environment times the system, that's going to give me, so the environment can be in some state. This is a column vector 1 0 0 0 times the system would be in some state. That's going to give me a gigantic column vector. But the bottom line is that this is going to give me sigma ek sum of all these EKs times the state of the system. So the state of the system was psi, let's say. So that's what I desire from my U. I have my U as, I start with a given state of the environment, which was 0 in my case, psi, and I should get a representation. Notice I can also apply psi to U to any other state phi of the system, and let's say I get some and if I take the inner product of these guys, I get nothing but this is going to preserve the inner product. So therefore the operator U, so this is just a representation whose matrix representation we've already given over here, that I fix one column of U that makes sure to the definition of tensor product that I am indeed getting this guy out here. And since by definition I defined U on only a fixed state, starting from a fixed state of the environment, and any vector or any state on the system itself, I can extend this U, make sure it is unitary, and I'm going to recover the unitary which is going to correspond to an operator sum representation on the system itself. So that's how I construct a U, by demanding this condition on U. And explicit construction of U would just require, as I've already said, blocks which are going to contain the operational elements. So notice that these guys, the operational elements EK, only determine the first column of U. By first column I mean the first block column of U. The rest of the matrix we have the freedom and it's left to us, and we'll just choose the rest of the matrix such that U is unitary. And then we are done. We were given these guys and we have constructed a U, and also demonstrated that this indeed is a unitary, and it gives rise to the operator sum formalism.